بس بدي أسأل لما أخذنا إنه لما نكون بحالة النورمال ونروح مثلا على الويت انستركشن أو على الستوب.
نعم.
هسا من الستوب لما بدنا نرجع على النورمال حكينا بدنا بنستخدم الانتربت الاي ار كيو والاي اكس
we can use the interrupt to exit the waiting state or the stopping state.
هسا بفرق لو استخدمت أنا سبروتين عادي أو مثلا جمب أو إشي؟
ما بزبط. ما هو
بس
the microcontroller is in sleep mode. The CPU is disabled. It's not executing anything. So you can't exit the wait mode or the stop mode unless some hardware trigger or event occurs, which is basically interrupt. And the type or the sources of interrupt that can force the microcontroller to get out of the waiting mode are different than those that get the microcontroller out of the stop mode. So just go to the slides. You can see what is the difference. As I remember that for the waiting mode, exiting the waiting mode can be done using any non-maskable interrupt in addition to the XIRQ. While for the case of the stopping mode, only IRQ, XIRQ, and reset can force the microcontroller or get the microcontroller out of the stop mode.
تمام, thank you.
Okay.
تمام.
Okay, so let me just go very quickly over the term paper assignment that we will do this semester instead of the project, unfortunately. I usually don't like this thing, the term paper, but we are forced to do it. The project is more meaningful for this type of courses because we are doing a lot of stuff in the theoretical part. We are explaining a lot of stuff related to the practical side of microcontrollers. So it would be better to do a practical project. However, due to the current situation, we cannot do that. So we'll go with the term papers. And what do we mean by term paper? Basically, it is kind of a short survey, a short critique paper where you read some papers, you summarize them, you critique them, you say, you question them. You say, why didn't they do that? Why did they do this? And you maybe put down some suggestions or some future work. And this is usually how we do research. Like when you want to do research, you usually pick some topic, then you survey the most recent and relevant papers related to this topic. Then you go through these papers and try to understand the topic, try to critique the topic, and try to build on that, on the work that is presented in these papers. So this is kind of an exercise to what you are expected to do when it comes to doing your thesis, inshallah, in the near future. So basically, you are required to pick and research some recent topic. So it's not only picking, you need to do some research in terms of reading, critiquing, questioning the papers in the field, in some topic related to embedded systems. At least you need to pick 2 papers that are related. The papers should be related to each other. They should be addressing or discussing the same problem. And these papers could be journal or conference papers. And they have to be recent papers. And I define recent in this course as papers published in 2017 and later. We don't prefer papers before that because newer papers give you better idea about what is going on in that field. Now, when you search for the journal and conference papers, please don't do that on Google because it will bring you a lot of rubbish papers, weak conferences, weak journals. So when you want to search for papers, go to trusted sources like IEEE, Elsevier, Springer, ACM. These sites can provide, you can search for papers based on a topic in these websites. And when you like some paper, you can search for it on Google for its PDF version, or you go simply search. There is a website, I don't know if you know it. It is called Sci-Hub. Just search for this website on Google. There is no fixed URL for it because they continuously change the URL. So search for this website on Google, and on that website you can copy and paste the digital object identifier of the paper or the URL of the paper that you want to download, and it will bring it to you. Mostly, for most paper, it works. It's very I don't want to say nice website, because they are hacking Elsevier, IEEE, all most publishing companies, they are hacking it, and their rationale is that papers should be open to everybody. That's why they keep changing their URL. So this website is important. You can download the paper from using this website. After you find it on Elsevier, IEEE, ACM, Springer, all these resources are trusted, and they publish quality paper, quality research paper, either journal or conference paper. I don't prefer and recommend using Google directly to search for a topic, because it will give you a lot of rubbish paper. What are you expected to deliver? You should deliver a report that summarizes the papers that you selected, and we will come shortly to the content of this report, and you need to present your paper. So this is also kind of practice to write and to present your work. It is individual work. Everyone has to work on his own, no teams. And the weight for this is 20 points. And I will come to the grade or points distribution by the end of this presentation. So what topics you can look for? This is the list of the topics. You can look for whether applications, real-time for on embedded systems, or topics related to embedded systems such as real-time operating systems, model-based control, fault-tolerant embedded systems, and so on. So you can, for example, power and energy optimization techniques in embedded systems, how to minimize power and energy, how to reduce power and energy, and so on. So some of you might be interested in security, the security of embedded systems and embedded networks, and so on. As I said, you need to deliver two things mainly, the report and the presentation, but also as an intermediate step, you need to submit a proposal. And the proposal weights 10% of the 20%, which is of the 20 points, which is 2 points. And basically, this is very short, let's say, report in which you write maximum, it is 2 pages, single space, 12-point font size, in which you just tell me what is the topic that you are going to research in, and you will put a list of references, and these references, they should include the 2 papers or the papers that you are going to consider in your study. And this is basically what I expect to find in this 2-page report. So this is a must, and it has to be submitted through e-learning. I will put a link on e-learning for this submission, and it is due in about 10 days, 9 days, something like this, before the lecture. So you upload it through e-learning. Don't send it to me by email. So this is a must. And you need to get my approval on this before you start working. So I will go through the proposal and tell you, yes, okay, go ahead, work on this topic, read the papers and do it, or I give you some suggestions and recommendations. So the report, as I said, you need to submit a report. The weight of it is 60% out of the 20 points, so it's 12 points, and you need to submit it by this date through e-learning. And here are the expected, here is the expected content, and it doesn't have, it can't exceed 8 pages. It is 8 pages using the IEEE conference format, which you can find here. So there is a template, which is the conference template for IEEE. You should use it to deliver your report. And finally, the presentation, it is 30% out of the 20 points. It has to be professional, maximum 20 slides, 15 minutes for presentation, 5 minutes for questions and answers. And we will come later as we approach this deadline, which is the week in which we will start doing the presentations. I will give you how I'm going to grade both report and the presentation so that you prepare yourself accordingly. So this is this kind of exercise. You may do it in other courses in this degree. I'm not sure who else does it in the program, but it is a common thing that instructors in the graduate courses ask students to practice looking for topics, searching for ideas, searching for papers, reading papers, summarizing them, comparing them, questioning them in order to exercise the idea of doing research. I think if you are registered, if you registered the seminar course, you are expected to do something like this. Who registered the seminar for this semester?
Yeah, yes, Doctor. Yes, you're right. We have a presentation.
Yeah, you have to do this. So this is kind of exercise. Okay, so this is all about the term paper. This is something general related to the course based on the current situation. So the university has put 2 scenarios. The first scenario is if we go back to school before the 1st of May, the grade distribution should be 50% for the final, 30% for midterm, and the rest is coursework. The rest is coursework. So what we will have here, we will have, if we go with this scenario, the 30%, 15% will go to the term paper, and homework 10%, quizzes 5%. But most likely, we are not going to go to school before 1st of May. This is this is what I believe. So we are not going to have a midterm. That's why I said the term paper is 20%, not 15%. But anyway, hopefully, if we go back before 1st of May, we will go with this. We will go with this arrangement or this distribution. Now, the second scenario that the university has set is if we go back to school after 1st of May, then the final is 70%. This is for undergraduate and graduate, 70%. But the Dean's Council allowed the College Council to change this 70%. So what we received from the College Council is for graduate courses, the final is 50%, and the coursework is 50%, and there is no midterm. So the distribution become, in this case, 50% for the final and 50% for the rest. And so we have 20% for the paper, 15% quizzes, 15% homeworks. And in both cases, in both scenarios, we will have 4 homeworks and 4 quizzes. 4 homeworks and 4 quizzes. So the second homework is posted. You submitted the first homework before we went off. And hopefully, when we go back, I can get the papers and give them to Muhammad to grade. Yes, Marwan.
دكتور, I just wanted to ask you, هلا نحن بالحالة إنه in both ways رح نرجع حيكون رمضان. So كيف راح تكون وقت المحاضرة؟
هلا بنتفق عليها يعني if يعني if we go back if we go back or if we don't go back before anyway if we go back to school it will be Ramadan so if it is Ramadan we will agree on some suitable time for all of us
Okay.
either online or personal physical okay so most likely we'll go with this but keep this in your mind hopefully we don't know if we will be able to go back by this time. All right.
ممكن أسأل دكتور؟
باسل تفضل.
لو رجعنا قبل 1/5 حتى ما فيش مجال نعمل بروجكت يعني؟
والله we'll see by that time. I thought about it actually. If we go back by 1st of May, I may leave it as an option for you. You may opt to do the term paper or you do the project. We may go by this option. But I'm not so optimistic that we will go back before 1st of May.
Okay.
But if we go by before 1st of May and you would like to do a project instead of the paper, yes, you can do it.
دكتور عادي أسأل سؤال؟
يلا بسرعة يا
اوكي بخصوص بس المواضيع او التوبكس انا يعني مش اشي بس هاي المواضيع يعني بيكون اي واحد الليستد التوبكس بيكون اي واحد انه قابل انه يفهمها.
Yes.
يعني
Yes. You need to. You should be able to understand it.
اوكي يعني ما بأثر انه
يعني نحن هلا we are taking the basics of embedded systems. So now if you go to some research topic, you should be able to understand it with some effort. Depends on the difficulty of the topic. Now, if the topic that you pick is more into an application, it will be more easier to understand. However, if it is something about like mathematical modeling of the power consumption in embedded systems, this might be more difficult for you to understand.
Okay.
Okay, and you don't need to stick to the topics that I just listed. You can pick whatever topic that is related to embedded systems. All right.
All right.
Okay. So let's go to. We finished last time chapter 6, right? Marwan, do you have a question? Marwan?
لا دكتور.
Okay. So last time we finished chapter 6, which was about interrupts, resets, the clock generation, real-time interrupt, all that stuff that is related to the HCS12 microcontroller. Now, what is left in this course related to the HCS12 microcontroller is basically going into some of the integrated peripheral devices. Some of the integrated peripheral devices that can be found in this powerful microcontroller, in this advanced actually microcontroller. So we will consider 3 or 4 peripheral devices. We will talk about analog to digital converters. We will talk about synchronous communication, SCI module, and some the timers and the counters. So let's start with the first topic, which is very important, the first peripheral device, which is the analog to digital converter module or peripheral device that is found in this microcontroller. And this topic is presented in chapter 12. So we will cover the basics. We will go over the basics of analog to digital conversion and the data acquisition system. Then we we'll see how this is implemented in the microcontroller in our hand, and we will see how to operate the integrated analog to digital converter, and we will go through some examples using assembly and using C. So basically, let's start with the basics of analog to digital conversion and what do we need in order to acquire data by microcontrollers. So basically, we know that microcontrollers are digital devices. In other words, they can understand and process digital data only. The input has to be digital and the output, and it has to be processed in a digital manner, and the output of the microcontroller is also digital. However, when it comes to designing embedded systems, we usually work with embedded systems. They work with non-digital data, such as non-digital data, which we call analog quantities or continuous quantities. And I think most of you know the difference, or what is the difference between analog and digital, right? Anybody, most of you took communications or are taking communications now, right? Anyone does not know what is the difference between analog and digital? Everybody knows that. That is excellent. So basically microcontrollers, because microcontrollers are digital devices, so they can process, they can manipulate digital data only. However, microcontrollers sometimes, or in most of the times, when they are used in an embedded system, in embedded systems, they have to deal with analog signals. They have to deal with analog inputs, such as temperature, pressure, light, and so on. And these quantities are analog, which means these quantities are continuous in time and continuous in amplitude. Okay, so the microcontroller cannot deal with this. The CPU cannot work with this type of signals, and these signals has to be converted into digital format. And hence, the topic we are talking about is analog to digital conversion. And this is what we are going to discuss in detail. Now, usually the quantities that I just mentioned, these physical quantities, such as temperature, pressure, light, all of the humidity, all of these quantities are non-electrical quantities. So in order to process them also, we need to transform them into electrical representation, and this is usually done using special devices which we call transducers or sensors. So usually if we want to, let's say, read the temperature by some microcontroller, we will use the A to D that is inside the microcontroller, which will take the reading from some sensor, and the sensor device, which maps the physical quantity into some voltage, So basically this sensor is an electronic device that is made from some material that is sensitive to the changes in the physical quantity that we are working with. For example, if we are working with temperature, then this sensor is manufactured using some material that it changes its physical attributes, such as conductivity or resistivity, when the temperature changes. So if you plug this sensor in some electric circuit, then this sensor will change the voltage that is coming out from this circuit, which can be mapped to the temperature. And this voltage is fed to the analog to digital converter, which transforms it or converts it to digital format. And knowing the relation between temperature and voltage and the converted value, we can know the outside temperature or the temperature of the environment. Okay, so we usually, in embedded systems, we usually deal with different physical quantities such as temperature, humidity, and so on, in order to read and make decisions based on these the values of these physical quantities. We need some sensor or transducer that gives us corresponding or proportional voltage, voltage proportional to the value of the physical quantity, then this voltage is analog. So we need to convert it into digital, and this is done using analog to digital converter. And most microcontrollers, they have the camera stopped, I guess. Okay, so most microcontrollers, not most, many microcontrollers, they have integrated analog to digital converter. Okay, so basically our interest in this chapter is about this peripheral device, which is usually integrated within the microcontroller and has the responsibility of converting signals from analog to digital format. So basically, the few coming slides are discuss the idea of analog to digital conversion process, the analog to digital conversion process, and probably most of you, they know that analog to digital conversion is basically 3 steps, right? 3 steps. What are these steps? In order to convert a signal from analog to digital, what are the 3 steps that you use? What is the problem with an analog signal like this? What is the problem?
انه دكتور ديجيتال هو فعليا بس بقرا 2 ستيج، يعني بس 1 0، ولما يكون عندي انالوج ممكن يكون في عندي اكثر من امبليتيود ماجنتيود للسيجنالز لازم اتعامل معها الكنترولر از ديجيتال.
يعني related somehow.
دكتور لازم السامبلينج تايم يكون اقل من هيك مشان اكون مور اكيوريت للسيجنال الحقيقيه اللي داخله علي.
ما هو شو what do you mean by sampling? Why do we need sampling? What is sampling? Like
sampling
if we
time انه يعني اقطع السيجنال.
Okay, if I consider some waveform like this, some signal like this that I monitor over this period of time. This is the time over which I am monitoring the signal. Now, if I want to process this signal using my CPU or using my microcontroller, then I have several problems. The first problem is how many points is there in this waveform that I need to process. Infinite number of points, right? We have infinite number of points, and my CPU will not be cannot process infinite number of points. How can I reduce the number of points? Basically, I can say I don't have to take all the points in this interval. I just take samples. For example, I take this sample, I take this sample, I take this sample, I take this sample, for example, and this sample, assuming that the number of samples that I took is sufficient and enough to represent the signal, okay? And usually we take sample, let's say every t. This is time. So we take a sample every t. So this is called TS, which is the sampling period, is TS. How often do you sample? What is the spacing between samples in time? And if you, and I guess most of you took signals, at least in your undergraduate course. What is the minimum value of this TS? What is the maximum value of this TS? What is the minimum number of points that I need to take in order to represent the signal? You don't remember sampling frequency?
ممكن أشارك بدك دكتور تضاف أو لا عفوا نص أكبر فريكونسي.
Okay, so إذا كان عندي أنا if I have the sampling frequency هو 1 over TS.
عفوا دكتور على المقاطعة، أنا عندي فريز الشاشة، عندي الكل هيك ولا بس عندي؟
هي في بروبلم اليوم شكله بالشاشة.
أنا مش شايف عم تكتب يعني.
Yes. You did not see all of this. Okay.
يس هلا شفنا.
تمام. هي شكله في مشكلة على الزوم. Okay, so I was as I said, if you have this waveform and you want to process it using a digital system like a CPU or microcontroller, then you will have infinite number of points in this waveform, and your CPU cannot process all of these infinite number of points. So what is the solution? Is basically to take a representative set of samples, okay, and then process these samples, assuming that the number of points that you took or the points that you took are sufficient to represent the main characteristics of the waveform. And if we take the samples every TS seconds, so if I write it like this, this is 0, this is TS, this is 2 TS, 3 TS, 4 TS, and so on. This is called the sampling period. And the sampling frequency is basically the reciprocal of the sampling period, which means how often do you sample the signal? How many samples you take per unit per second? This, I said, is there any guideline? What is the value of the sampling frequency? What is the value of TS? If you remember from your signals course, this has to be greater than Fm, right? F max or 2F max. باسل.
أنا بتخيل نص F max.
نص F max ولا twice F max؟
لا بتخيل نص بس I'm not sure.
لا ما هي F يعني أنت مذكر you remembered it the other way around. ميمونة.
هي بتعتمد على نايكوست ريت بالعادة هو دبل الفريكونسي للسيجنال نفسها.
Yeah, فالنايكوست ريت هو twice FM. What is FM? It is the maximum frequency content in the signal. If you convert this to frequency domain, then you can find FM. So in order to be able to represent this signal using its samples, you have to sample at this frequency. You have to sample at this frequency. So the maximum frequency is half the sampling rate, or the sampling rate is twice the maximum frequency content in the signal. Okay, we don't want to talk to give more details about this, but this is just for your information. So the first idea or the first problem that we had is the infinite number of points in the input signal, and we solved this using sampling. So the very first step in A to D is taking sufficient number of samples, Now, when you take the samples, there is another problem that comes around, and this problem is basically related to the magnitude of these samples. For example, if you take the sample here, the value will be 0. If you take it here, it will be, let's say, 1. If you take it here, it will be 1.5. If you take it here, it will be 1.25, and so on. So what is the problem here is the values of these points or samples can be any value. right? Can be any value of any, with any number of digits. It could be negative, it could be positive, it could be 1.05, it could be 1.025, and so on. So what does this imply? This implies in order to store the values of these samples in your computer, you will need infinite number of digits because the sample may take any value. So how can we solve this problem? The first thing is we need to set a minimum value, V minimum, and a maximum value through which we observe the sample, because we can't observe an infinite range, right? We can't observe the whole range from -infinity to infinity. So usually we put a minimum and a maximum, so we define a window or a range through which we observe the samples. However, even in this range, we have infinite number of possibilities, right? We have infinite number of possibilities. So what we usually do, we divide this range into sub-ranges like this. So we say all the points in this range are mapped to 0. All points in this range are mapped, let's say, to 1. All points in this range are mapped to 2. All points and above are mapped to 3. We can do something like this. So essentially, if we do this, we are working with samples that can be either 0 or 1 or 2 or 3. Okay, assuming, for example, here that mean Vmax is 3 and V minimum is 0. V minimum is 0. So to solve the problem of having infinite number of values that I can use for these samples, I first limited the range, then I divided the range into sub-ranges, and I said all the values in this range are mapped to the minimum value, all the values in this range are mapped to the minimum value, all values in this range mapped to the minimum value, all values and above are mapped to what? To the 3. This process is very important in order to have finite number of values that these samples can take, because I can't work with infinite number of possibilities. Because if I want to allow the sample to take any value from -infinity to infinity, then I need infinite number of digits to represent the values of the samples. So what we did here is somehow similar to what we did here. We limited the number of points. Here we limited the number of values to be used by these points. And this process is called quantization. This process is called quantization, which is the second step in analog to digital conversion. It is the second step in A to D. So basically, we define a minimum value, maximum value. Usually they call it V reference low, V reference high, or V minimum, V maximum. Remember these two values. And then we divide it into certain number of sub-ranges. Now, the more the sub-ranges that you use, the better is the accuracy, because the error will be less. For example, if you use 8 sub-levels, then the error will be less. What will determine the number of sub-ranges basically is the third step, which is encoding. In which you need to encode these sub-ranges into binary. So if you want to have 4 ranges, 4 sub-ranges, or 4 quantum levels, then how many bits do you need? 2 bits. You say 0, 0 is voltage 0, 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. So this is the number of bits that you use to encode these levels in binary basically determines the number of sublevels. If you use the 3 bits, then you will have 8 levels because it is 2 to the power 3. If you have 4 bits, you will have more sub-ranges, and the more the bits you use, the more sub-levels that you will have, and the less is the error. The error will be less when converting the sample. So this is very important in coding, which is basically representing the sub-ranges into binary, and this is a main attribute of analog to digital converters. Usually, you will when you go to buy or to use an analog to digital converter, it tells you it is an n-bit analog to digital converter. What do they mean by n-bit? They mean that this A to D uses n bits to represent the converted values. In other words, it has 2 to the power n sub ranges or sub quantum quantization levels. Okay, so 3 steps. You need to sample to reduce the number of samples that you are working with, to reduce and limit the number of samples. Second step, you need to quantize. In other words, you can't deal with infinite number of possibilities along the vertical axis. So basically, you choose a range here, then you divide it into sub-ranges. And the third step, you encode it into binary. And the number of bits that you use in coding basically determines the number of sub-levels that you have. So this is very quick overview. Here, for example, we have an example on an analog to digital converter, which is a 3-bit A to D, because we have here the representations. And here it tells us that the V maximum, this is V maximum or V reference max, it is 8 volt, so which is this one. And the minimum is assumed to be 0. So if you have this range from 0 to 8, the maximum is 8 volt, and you use 3 bits. You use 3 bits to represent the sub-ranges. How many sub-range will you have? How many sub-ranges? 2 to the power 3. So you will have 1, 2, 3, 4, 1, 2, 3. So these are the ranges from 0 to 1, 1 to 2, 2 to 3, 4, 5, 6, and 7. Okay, so any value that at the input, this is the analog input here, any value between 0 and 1 will be represented as 0, 0, 0. Any value between 1 and 2 will be represented as 0, 0, 1, and so on until we reach 1, 1, 1. So this is the convergent, let's say, table for different input values. Now, any value less than 0 will be mapped to 0. Any value greater than 7 will be mapped to, any value greater than 8 will also be mapped to 1, 1. Because anything above this maximum value will be also mapped to the nearest lower value. Okay? Okay, so this is the basic idea of the A to D process and the steps involved in the A to D process. And I want to stress on the idea of this n-bit A to D. It implies that the A to D uses n bits to represent the value of any samples that it collects. For example, this point is in this range. So it will be converted to 0, 0, 1 because it maps to 1, so it will be converted to 0, 0, 1. N bits implies that you are using, or the A to D uses 2 to the power n sub-levels or quantization levels. The more the n is, the better the accuracy and the less is the error. Okay. Now, if you go to yes.
عادي اسال بس بخصوص الفي ريفرنس حكيت انها هي 8 فولت، مش انا راح يعني الرينجز هذول مش بيعتمدوا على الانالوج انبوت فولتج؟
Yes, هلا هدول يعني this is an example on the slide. It is an example where the maximum value is set to 8 and the minimum value is set to 0.
Yes.
Okay, and usually, as we will see later, these two values, the clipping values, has to be selected such that they match the possible input values. For example, if the input voltage varies between 0 and 1, it is inefficient to pick the reference voltages to be 0 and 3 because all the input values will map to 0.
Yes.
Okay, so this we will talk about it in a bit. Picking the reference voltages is usually based on our knowledge about the input signal, the analog input, the range of the analog input values, and we try always to make the reference voltages match the minimum and the maximum of the analog input to the best we can in order to increase the accuracy and utilize the input, the reference range. Okay?
تمام.
Okay. So if you are going to work with analog to digital converters, usually you will find that these converters, they have some let's say common attributes or characteristics or features. And the first thing, we already talked about it, which is the reference voltage. So when you want to use an analog to digital converter, usually you will find that this A to D has two inputs, two dedicated inputs, usually, but not necessarily. That this A to D has whether it is a standalone A to D or whether it is inside some microcontroller. You will find that there are two inputs. They call them sometimes Vmax, Vmin. Oh, that's me. So we have this Vmax, Vmin, which basically define the clipping range or the range that you are interested in, as we saw earlier. And these are called the reference voltages. They determine the acceptable range of the input voltage. Out of range input values are clipped. In other words, values less than V minimum are mapped or clipped to V minimum. The same thing for values greater than Vmax, they are clipped to Vmax. Now these reference voltages, they could be unipolar or bipolar. In other words, Vmax and Vmin, they could be both positive or they could be both negative, or both they could be positive or negative, depending on the design of the A to D. For example, some A to Ds, they are unipolar. In other words, V minimum and Vmax can be only, let's say, positive, and usually this is the case. Or they could be unipolar or bipolar. So for example, you can say this is +5, for example, and this is, let's say, -3. Or this is -5, this is -10, for example. So how do you pick the values? Depending on your analog input. What is the expected range of the input analog signal? You pick the values that best match the range of the input analog signal. So this is one important thing or attribute of A to Ds. Another attribute is the resolution. Okay, just a second. Okay. So is the resolution, and by resolution, basically, we mean the amount by which the input, sorry, yes, the amount by which the input voltage, why it's, oh, okay, sorry, the screen is not, the amount by which the input voltage has to change to go from one output level or output value to another. So if you remember, like in the previous example, we had a 8 volt, 0 volt is the minimum, and we had 8 sub-levels, right? We had 8 sub-levels. Now, what is the width of each sub-level or each quantization level? It is basically 8 minus 0 divided by 2 to the power n, divided by 2 to the power n. And what is this? This is called the resolution. So it is the amount by which, if you increase the input value by this value, you will move from one sub-range to another sub-range. So if your input sample is here, if you increase it by this value, which is this distance, it will move to this level. So this is called resolution, and it is basically, as I did here, it is V max minus V minimum divided by 2 to the power n, where n is the number of bits that are used to represent the samples. So this is the resolution, which is one step or the width of one sub level. Okay, so this is the resolution and how to calculate it. And there is another thing related to the resolution, which is the quantization error. And I will not go into much details about it, but if I consider the same example, I say this is my input range from 0 to 8. So I have, and let's assume we have 3 bits. So we have 8 sub-levels. So if I have an input sample that is actually here, this is the voltage of the input sample, but due to this, it will be mapped to here. It will be mapped to here. So effectively, it is assigned to 0 volt, while its value was, let's say, 0.8 volt. So there is an error, which is this. And this error is due to quantization. And the value of this error is, quantization error is 0.8 volt in this case, because actually the signal is 0.8, but it was mapped to 0 volt. So the error is the actual value minus the mapped value, which is 0.8 in this case. So this is related to the quantization error. What is the maximum quantization error? Which is this. Let's assume that the input is here, is very close to this, and it is, so it will be mapped to here. So maximum, the quantization error is basically the resolution. Maximum is the resolution. However, here it is written that the quantization error is resolution by 2. Resolution divided by 2. And this is something related to the following. I removed it. So forget about this. We will just consider that the quantization error is basically the resolution. And here, when I say the quantization error, it means the maximum quantization error, because the quantization error here, for example, is 0.8. Here, the quantization error is 1. So the maximum quantization error is the same as the resolution. Okay, one more thing is related to the conversion. For example, given this, let's say, analog to digital converter, where we set this to V minus This is V plus, two values. Or let me be consistent with the slide. This is V reference low, and this is V reference high, which are fed to here. And we have here an n bit A to D. And I tell you that the input value is Vk. So here at the output side, we have n bits, let's say bit 0 up to Bn minus 1. So this is the output, the digital output of the corresponding input value, the corresponding input sample. And I tell you what is the output if the input is Vk. What is the output if the input is Vk? Anyone has an idea? Given this setup, this A to D, if the input is Vk, what is the digital output? We call this the digital output, or the digital representation of the input sample. The input sample. Anyone has an idea?
مش متأكد أنا، بس يمكن VK minus V reference low over the resolution أو إشي زي هيك.
Yeah, usually as it is written here, most analog to digital converters are ratiometric. In other words, the input and output are related to each other as a ratio. So it is something like this. We assume that the ratio is linear, or the relation is linear. So we say when Vk is equal, let's say this is Vk, and here is the output. So when Vk is V reference low, we want the output to be 0. When Vk is V reference high, we want the output to be 2 to the power n minus 1. Here I'm writing the decimal value of this output, but at the end it is digital. So if I tell you that this is the mapping of Vk to out, what is the line equation that represents this relation? This is the input, this is the output. So you say you have a line that defines the relation between Vk and the output. What is the relation? What is Vk if you know V out, or the opposite? What is V out if you know Vk? So let's take it from out to Vk. If you know the output, the digital output, or the digital representation of the signal, what is Vk? What is Vk? Okay, what is Vk? So Vk is y and out is x. So the points that we have, 0, VRL, and 2 to the power n minus 1, VRH. So if you have these 2 points and you want to find the line equation, the slope will be what? VRH minus VRL divided by 2 to the power n minus 1, right? Then what is the line equation? This is the slope. This is the dependent variable. So this is out minus 0. I take this point as my reference, equals Vk minus VRL. Very simple line equation. So this is Vk equals VRL plus, what is this? VRH minus VRL. If you go back, it is the range, or the input range. It is the input range. So that's why it is, we write it range divided by 2 to the power n minus 1, out minus 0, which is out. Okay, so this is the equation that relates the digital output with the input analog voltage, or the input analog voltage with the digital with the digital output. It is the same equation that is on the slide, but here out is called K, which is the digital or the binary representation of the input. So using this equation, we can either calculate out from Vk, or we can calculate K, which is the digital representation, or we can calculate what was the input voltage if we know the digital value. And this is what we usually do in embedded systems. When we do the conversion, we have K inside the microcontroller, but we don't want K. We want what is Vk. So we do this arithmetic operation inside the microcontroller in order to calculate Vk. Because if the output is 0, let's say is 10, or the output is, let's say 112, K is 112. Does this imply that the input is 112 volt? No, this means that we have moved 112 resolution steps from starting from where? From VRL. Remember this that I drew here? We have VRL here, we have VRH here, and we have sub-levels. So the digital value that we get here is basically how many steps we moved from this reference voltage. So if you want to know this value, we basically take this, multiply it by the size of the quantization step or the resolution in order to get to this point. So this is very important. The examples we saw earlier for the 3-bit converter was like tailored example, because the reference voltage was from 0 to 8, and we have 8 levels, so the step size was 1 volt. So the digital output was the same as the input value of the sample. However, this is not the case. Generally, the value that we have for K is basically how many steps did we move from the minimum reference voltage in order to get here. So this is the number of steps, 112. So what does this correspond to as a voltage? We multiply it by the range or the resolution. We multiply the number of steps by the resolution. We add it to the reference VRL to get Vk. This is Vk here. Okay, so this is very important. You will need this when it comes to programming the microcontroller to process the acquired sample. So here we have a sample. We take one sample, we give it to the analog converter, and it produces the corresponding digital output. Okay, an important note here is this, which is in red, which tells us that to have a more accurate result or convergent result from the A to D, the analog signal should cover the whole voltage range from VR to from VRL to VRH. And this is, we already talked about, the best values for V low and V high, or V max and V min, VR reference high, V reference low, to match the minimum and maximum value for the input signal. This will give us the best accuracy in terms of error. We have the least error, and I usually like put this simple example. Let's assume that your input, that your A to D has this, it has from 0 to 4, and it is a 2-bit converter. So we have 1 volt, 2 volts, this is 3 volt, 4 volt. So we have this range, and this range, and this range, and anything above the 3 will be mapped to 3, anything below 0 will map to 0. Now, if our signal V input is in this range from 0 to 0.5 only, This is our analog signal, and usually the sensors, they produce low voltages, sometimes in the millivolt range. Most sensors, they produce low voltages. So given this scenario, if you feed this analog signal to this converter, which has this characteristic curve or this characteristic mapping, what will be the output of the A to D? Note that all the values will fall in this range. So all of them, they will be mapped to 0. So the output of the digital converter will be always 0, despite the fact that the signal is changing. How to overcome this problem? If we set this to 0 and we set this to 0.5, so this will be 0.125, 0.1.25, this will be 0.375, and this will be 0.5. So now the signal can cover the entire input range or the entire reference range of the A to D, and the A to D will produce better result. So the rule of thumb is the reference voltages should be chosen to match the input voltage range. The voltage range of the input signal to the best we can. Sometimes we don't have control over these voltages because they are taken from the system voltage. We can't change this. So the alternative is to fix this and change this. And how can you change the input voltage of the signal? So if you can't, let's assume that you can't change the reference voltages because these are fixed. These are the only voltages that are available in the system. How can you use the A to D and get the best results? Basically is to manipulate the input signal. For example, here in this case, if we manipulate Vn to produce Vn prime such that Vn prime is in the range from 0 to 4. So basically, if you multiply this by 8, so you process this, and this does not require you to change the input voltage. How to do this? How can you multiply an analog signal with 8? وين جماعة الإلكترونيكس؟
Because تحتاج amplifier.
Yes, exactly. Analog signals can be manipulated using amplifiers, operational amplifiers. And this is discussed later in the slides. So this can be done using an op-amp. You bring an op-amp plus minus something like this. So this is Vn, you get Vn prime by selecting proper values for the Rs. Okay, so this is discussed later in the slides. I will leave it to you to remember the electronics that you studied in your undergrad. Another problem, if we have something like this, if you assume that the input range is from 0 to 4 volts. However, Vn, let's say, is in the range from -1 to 1. From -1 to 1. Now, if we don't want to change the reference voltages, then we have to transform or manipulate this signal such that it maps to this range in order to maximize the benefit. And how to do that? We have here negative values, right? We have negative values. And these negative values, if fed into the converter, they will all map to what? To 0. So what we want to do, we want to produce another signal called Vn prime, which is Vn plus 1 to make all values from 0 to 2, then you multiply it by 4. Then you multiply it by 4. And how to do these two operations? Shifting, level shifting of the analog signal, then multiplying by 4. it is also using op-amps, operational amplifier, and this is also discussed in one of the slides that come next. Okay, so this is called usually signal conditioning. You condition the signal, you pre-process the signal in order to, let's say for our case, to match with the input reference range. All right, okay. So this is an example how to use this formula on this slide, how to calculate VK if you know K for the case, for example, when V reference low is 1 volt, V reference high is 4 volts. So just to go through the numbers, it's not difficult. Okay, if you just, I need 5 minutes if you allow me. Another attribute of the A to D, when you want to go and buy an analog to digital converter, or you want to use an analog to digital converter, one important thing is the conversion speed. How fast does the A to D produce the result? How fast does the A to D produce the result? And this varies depending on the way the A to D is designed and implemented. Some A to Ds are fast, some A to Ds are slow. However, faster A to Ds are of less accuracy, while slower A to Ds are of higher accuracy. So it is a trade-off. So you may find fast A to Ds, but however, these A to Ds, their accuracy is less than the slower ones. Okay. Another attribute of A to Ds is the digital interface. And as we said, this analog to digital converter is usually the interface between the analog world and the digital world. In other words, it is connected to the digital system, to a digital system in the digital world. And it has to be controllable using this digital system, which is in our case, the CPU inside the microcontroller. That's why most A to Ds they come with what we call the digital interface, which is basically a set of inputs and outputs through which the CPU can communicate with the with this A to D in order, let's say, to start the conversion process, to know if the conversion process is over or complete, and so on. So here, for example, we have this input, SC, which is a start conversion. We have this output, which is end of conversion. So basically, the system that is connected to this A to D can instruct the A to D to start the conversion process by setting this input to 1. And it has to wait for the A to D to finish the conversion, and it knows that the A to D finished the conversion when it sets this output, let's say, to 1. So this is called the analog, or sorry, the digital interface, which are basically inputs and outputs used to interface it to some digital device. Okay, so this is a very quick overview on the A to D process, some of the A to D converter features of the A to Ds. Next time we will discuss the acquisition system. Usually, when we want to acquire some signal, when you want to convert some analog signal into its digital format, you will need an analog to digital converter. However, it is not the only thing. This A to D will be part of a bigger system, which we call the acquisition system, which is usually required to do other tasks in order to perform the ultimate goal, which is the conversion. The converter, the A to D converter, is just responsible of taking one sample and producing its corresponding digital representation. However, to reach to this point, we may have to do a lot of stuff before doing that, and this is what we will discuss next time, which are the components of the data acquisition system. So this is basically what we are going to discuss next time. This is the A to D, which is part of the data acquisition system. However, we will need some other things in order to have things work in a more efficient and more reliable manner. Okay, so we'll discuss this next time. Any question? All right. Last time you took one quiz, which is quiz 1. I'm thinking of having another quiz next Monday or Friday. Monday or Wednesday, sorry. Wednesday?
Yes, لو Wednesday أحسن دكتور.
طيب, so quiz number 2 is on Wednesday, which will be شو اليوم 6 8 15. It will be 15, which is the same date as the date of submitting the proposal. Okay? So you have almost 1 week to do the proposal and prepare for the quiz. And don't forget that the second homework is due on Wednesday, this Wednesday. What was what? It is due this Wednesday through e-learning. You need to click on e-learning and you can upload the your solution through e-learning.
بس الكويز بأني مادة؟
Chapter 4 and 5.
Okay.
Let's leave 6 to the third quiz, which is the interviews.
Inshallah.
Okay. So homework number 2 is due on Wednesday. Quiz number 3 is on Wednesday, 15th of April. Okay.
دكتور
Yes.
بالنسبة للproposal, aren't we supposed to, when we give it to you, to approve it, then we